SwayamPrabha. Digital India. Educated India.
In the previous lecture, we started with analysis of composite laminates which are piezoelectric patches, and we did the analysis using the Galerkin technique. Now, because there are piezoelectric patches, there were terms like NPX, NPY, NPS, similarly MPX, MPY, MPS, which we are yet to define, and these terms come because of the free strain in the piezos. Now, to define these terms, first we need to define the free strains. Now, free strains are the ones which, if we set the piezoelectric patch free and then under some electric field or voltage, whatever the strain that happens, that we call as the free strain. And then if we try to block it, then the amount of force that is generated is block force, or the corresponding stress we can call as block stress. So, here we have a piezo patch which is in 2 dimensions, and we need to find out the free strains in both x and y. We have nothing in z direction, and that will have normal strain along x, y, and shear strain along in the xy plane. So, we have, and this we can call epsilon p x y also. So, these are the free strain components, and from the constitutive relation, if we take only the relevant part, it looks like this. E3. If we look at the constitutive relation that we defined, and then if you take the relevant part of it and remove rest of the components which are leading to other strain components, like any strain component in the z direction which we do not need, then rest of it looks like this. Then finally, the strain components are zero. Now, please understand, this material is isotropic in the xy plane. So, that is why D32 and equal to D31. So, this tells me that the free strain, there is no free shear component of the free strain, and there are 2 normal components and they are both same. So, we can define that as just epsilon p as well. Epsilon p y, and that is equal to D31 E3. So, now we can define the stresses also. So, if this strain is, if this stress is prevented, sorry, if this strain is prevented, if the material is prevented from any deformation, then the stress that is generated, we can call it a block stress. That would look like this. Now, this is the constitutive relation, assuming that there is a plane, the plane strain condition exists. So, plane stress condition, not plane strain condition, because these are the thin patches, or our composite plies are also very thin. So, we consider plane stress condition in our composite plies as well as in the piezo patch. So, this is the constitutive relation for the plane stress condition. So, nu EC is elastic modulus, we have already dealt with, and nu is Poisson's ratio. Now, finally, if we simplify this expression, it looks like this. So, these are the stresses. So, we can call these as block stresses. So, accordingly, there will be block force. So, the force corresponding to these stresses are called block forces. Now, here we will find out the forces per unit width. So, previously we had a beam problem, and when we are solving the beam problem, our beam was looking like this. Its width was much smaller than the length and other dimension. So, we are finding out the stress resultants Nx, Ny, Nx, Mx and everything, or the corresponding Nxp, Mxp everything at one section, at a section like this. But here instead of that, we will find it these forces or moments per unit run along the width direction. So, we will integrate these quantities along the thickness only, we will not integrate it along the width. So, if we define the corresponding forces in SP, this becomes sigma xp, sigma yp, sigma sp dz, where z is the dimension along the vertical direction. And please understand, this composite patch is mounted on a composite laminate. We are only integrating over the thickness of the patch. And if we say that the thickness of the patch is Tc, then the block force becomes sigma xp Tc, sigma yp Tc, sigma sp Tc. T is piezo patch thickness. Now, we have already defined these quantities. So, these are 1 minus nu, and then we have D31 E3 Tc, D31 electric field Tc and 0. So, these are my Nxp, Nyp and Nsp, which we used in our formulation. Similarly, there can be corresponding momentums, and these we can denote as Mxp, Myp and Msp. Msp is also Mxyp. Similarly, this is also Nxyp, and this quantity is minus z sigma x p sigma yp sigma sp dz. So, if we assume that we have a composite laminate which looks like this in the xz plane, and we have a piezoelectric patches at the top. So, this is a laminate, so it can have several layers. Now, this part is let us denote this part as Tb, like we have been doing. So, this part is the thickness of the laminate, and this is our thickness of the piezoelectric patch TC, and then if we assume that they have similar property and they are actuated using opposite voltage, then accordingly we can find out these quantities, and that becomes our the corresponding moments. So, this becomes epsilon p E c by 1 minus nu, we can multiply d31 E3 here, and then we have TB plus TC, TB plus TC and 0. So, these are the corresponding MXP, MYP and MSP, and this we used in our Galerkin formulation. Now, we will solve the similar problem using the Rayleigh-Ritz approach. So, in the Rayleigh-Ritz approach, again we assume that our displacement components are approximated by this basis function. So, u0, which is the mid plane displacement along x, is only a function of x and y, and this we get as phi uj multiplied by q uj. Phi uj is a known function of x and y. Similarly, we have v0 and w0. Now, we put this thing in our energy expression. So, this is our variational indicator. This is analogous to the virtual work principle. So, here we have a inertia term. So, this formulation we are doing keeping it more generic, so that if the problem is time dependent, if it is a dynamic problem, this can also be solved. So, rho is the density of the material, and then we have this variation of the displacement components and multiplied by the accelerations, and here we have the variation of strain multiplied by the stress, and here we have the virtual work due to the applied forces, and this is equal to 0. That is what the principle says. Now, u we know it is u0 multiplied by z into del w by del x. Similarly, v we know it is v0 multiplied by v is equal to v0 multiplied by z into del w by del y. So, that is what we are putting here, and that is how all the terms are written. Now, we can write these things separately. So, u0 multiplied by this and v0 multiplied by this is written separately here, and rest of it is put here. So, this term is broken into two parts here for the sake of doing some mathematical manipulations. Then if we evaluate those integrals, and then finally after integrating we get the terms to be mu0 double dot del u0 plus mv0 double dot del v0 minus s w comma x double dot del u0 minus s w comma y double dot del v0, and then we have minus s u0 double dot variation of del w by del x minus s v0 double dot variation of del w by del y plus m w double dot del w plus I w comma x delta of w comma x plus I w comma y delta of w comma y, and this entire thing is integrated over the two dimensional domain. Now, here m is the integral of rho along z. So, if I integrate this density along the z, whatever we call it m. So, in some sense it is mass per unit area. Similarly, we have S, and which is z rho dz, and we have I, which is z square rho dz. So, what we have done is there it was a volume integral. So, after integrating the quantities over the depth, we have got rid of the depth z dimension, and it is converted to a surface integral. Now, these terms can be rearranged and written in this way. So, if you can look, when this gets multiplied with this matrix, we get a term like m u 0 double dot, and then it can get multiplied with del u 0. So, m u 0 double dot del u 0 comes from here. Similarly, we get m v 0 double dot and del v 0 that we get here, and accordingly we can verify that this term is a compact version of this entire expression. So, here we have the variation of u 0 v 0, here we have the variation of w and its spatial derivatives. So, this is the same thing written here. Now, we have already written u 0 and v 0 in terms of these phi's and q u and q v. So, we can write this in a matrix forms as this. So, we can take this vector which consists of q 1 to q m and q u 1 to q u m and q v 1 to q v n, which we put as one vector, and when this gets multiplied with this matrix, we get u 0 and v 0. So, the terms from q u 1 to q u m gets multiplied with phi u 1 to phi u m, and after being summed up it gives us m u 0, that is our approximation, and similarly we get v 0 here. Now, let us define this vector as q I. Here I stands for in plane. So, anything that involves u and v or u 0 and v 0, we will call it, we will put it put there subscript of I means in plane, and anything where like here we have components of w, we will call that q w, and let us call this vector as let us call this matrix as n I. So, we have u 0 v 0 as a row vector here, which means it is a transpose of this vector. So, this can be written as delta of q I t multiplied by delta of n I t. So, this is u 0 v 0 is n I multiplied by q I, and if I want to take a variation of it, these terms, because these are all known to us, it cannot be varied. So, this can be varied. So, it is n I multiplied by variation of q I, and then when we take a transpose of this, they interchange their place. So, it becomes delta of q I t multiplied by n I t, and then this matrix, let us call it m I I. So, it is m I I, because we are putting two i's, because at the both side we have only the in plane component. So, it is m I I, and then again this is n I multiplied by q I double dot, because u 0 and v 0 is q I multiplied n I multiplied by q I. So, u 0 double dot v 0 double dot is n I multiplied by q I double dot. So, that is what we have put here. Now, let us come to this term. If we look at this term, again we have delta of q I multiplied by q I transpose multiplied by n I transpose. Because of this matrix, let us define this to be m I w, because it is at its left side we have the in plane components, at the right side we have the out of plane w components. So, it is m I w, and then now comes this. So, this matrix this vector w comma x w comma y, we can write as this based on our approximation. So, this matrix we call NW and this vector we call QW. So, that is, and similarly when we take double dot here, this NW remains NW and a double dot comes in QW. So, it becomes NW multiplied by QW double dot. Now, if you look at this, so here we have W, W comma x, W comma y as a row vector. So, this has to be transposed. So, and its variation has to be taken. So, delta Q W transpose comes here, NW transpose comes here, and then we have this matrix and this we call NW I matrix. The reason is we have at the left hand side we have W terms, at the right hand side we have the in plane terms. So, we call it MWI matrix. Now, we can see that this MWI is transpose of MIW, and then in the right hand side U0 dot, U0 double dot and V0 double dot. So, it is NI multiplied by QI double dot. Now, let us come here at the last term. So, here we have W, W comma x, W comma y, it is transpose. So, it is, as we know, it is a variation of QW transpose multiplied by NW transpose, and this we call MWW, because at its left we have W terms, at the right we have W terms. So, it is MWW, and as usual we have NW transpose multiplied by QW double dot. So, this is our MWW and this is our MWI. So, that is how the inertia related terms comes out to be. Now, we need to deal with the terms that has the strain and stress. So, we know that the strain epsilon consists of epsilon 0 multiplied by z into kappa. So, this delta should not be here because we already have a delta. So, z multiplied by kappa, and then it is transposed and then it is multiplied by the stress. So, stress is nothing but Q multiplied by our strain terms, and from the strain terms we need to separate out the free strain terms. So, that is what we see here. Now, if we multiply this del epsilon 0 with Q and epsilon 0, so del epsilon 0 multiplied by Q into epsilon 0. Now, please understand this Q matrix for each ply is different, and even we had a Q matrix for the piezoelectric patch also after applying the plane stress condition, which was E by 1 minus nu square, and then a matrix of 1 nu 0, nu 1 0 and 0 0 1 minus 0 0 1 minus nu by 2. So, those are all Q's for each and every layer. Now, if we want to convert this to a surface integral, we need to integrate these terms over the depth z. Now, this term does not depend on z, it is independent of z, this is independent of z, only Q is dependent on z, and we know that when we integrate Q over the thickness of all the layers, that gives us a matrix. So, it becomes del of epsilon 0 multiplied by A matrix multiplied by epsilon 0. So, this is this was wrong, excuse me for that, this is del V over volume, and then we get this. Similarly, when we get a term like delta of epsilon 0 multiplied by Q multiplied by minus of z k, we get delta of epsilon 0 B and it is a kappa. So, delta of epsilon 0 multiplied by Q multiplied by minus of z kappa, then we get a term like delta of epsilon 0 B multiplied by kappa, because minus z multiplied by Q on being integrated over the thickness gives us the B matrix. Similarly, we get another term consisting of B matrix, because we have Z kappa multiplied by Q into epsilon 0, and this term where we are multiplying Z kappa variation of Z multiplied by variation of kappa into Q into Z kappa. So, there is Z square into Q, and that on being integrated over the thickness would give me the D matrix. So, we get this term. Finally, we have this epsilon 0 multiplied by Q multiplied by epsilon P, and that gives us the NP matrix, which we already derived. Now, our epsilon P is valid only for the piezoelectric patches, the in between the composite laminates, the composite plies, they are not active. So, they do not have epsilon pi, they do not have epsilon P. So, that gives us NP. In fact, it is a vector, and then we have MP, because we have minus Z and Q and epsilon P, they are multiplied, and on being integrated that will give me MP, which you have already seen. Now, our job is to relate these epsilon zeros and kappas with the approximations that we made. So, epsilon 0, as we know, is del u 0 by del x, del v 0 by del y, and del u 0 by del y plus del v 0 by del x. So, if we put the if we use the approximation, this entire thing looks like this, or this vector looks like this. So, this again let us define this as B I. Now, we have a B matrix here, and that is basically that relates, that comes from integrating the composite integrating the properties along the z direction. So, it couples the moment and the in plane components. So, that is a stiffness component, and here we are putting B with suffix I, but this is nowhere related to this B. So, this B I is relating our strain components with the displacement approximation, the constants associated with the displacement approximation. So, it is B I multiplied by this, we already know it is Q I. Similarly, the kappa matrix becomes if we use the approximations that were made for kappa, it looks like this, and here we have phi and this entire matrix is multiplied with Q W 1 all the way up to Q W P. So, this is B matrix, we would like to call it B W because it involves the W components, and this as we know it is Q W. Again, if we put all these definitions, then we have epsilon 0 transpose and its variation. So, this looks like this, A matrix remains A, and again we get this. Here we have epsilon transpose, its variation. So, same thing, and here we have a B matrix, and then here we have kappa. So, kappa is B W into Q, and this is delta K transpose. So, this thing just gets transposed here, and on being transposed they change their places, this Q W and B W, and Q W is has a variation delta. Then B multiplied by the epsilon 0, and here this comes from this term where you have the transpose of kappa, D and kappa. So, again please excuse me, we should not put so many variation symbols here. So, this variation symbol, this variation symbol, and this variation symbol is not, should not be here, variation should be only in these terms, and accordingly we should not put variation here also. Now, here we have the variation of epsilon 0 and its transpose and NP. So, NP remains as it is, and variation of epsilon 0 comes here, and here we have variation of kappa, its transpose, and this comes here, and here we have MP. So, this is about how it looks if we expand the terms and put all the approximations in delta of epsilon t multiplied by sigma, its volume integral, that is how it looks. Now, we have to take care of the force terms. The force are applied at the surface and we assume that we have distributed forces Px, Py and Pz. So, this is Px, Py and Pz, and this looks like this. So, this term after we break it up, it would look like this. And we have already made some approximation. So, this is Q I T multiplied by N I T, and we have P x P y and here for del W we can call this as N W 1 transpose of it. Okay, we need to put the transpose. And here we have NWT. So, where NWT NW is phi dot 1 to phi dot p, because we know that our W is this as per our approximation, and we are calling this as NW. So, we have taken care of the inertia terms, the force terms and the internal virtual work terms. Now, we need to put everything together and get the final equation. So, that we will do in the next lecture. Thank you.